Hello and welcome. Eamonn Darcy is my name. I'm the founder and director of Qbism, the Quantum Education Centre of West Australia. Please subscribe to the channel or like the video. It does make a difference. We're already halfway through. We're up to video lesson 5 out of 10-minute video lessons on quantum physics and quantum computing. You know, if you just dedicate 10 minutes every so often, after you've done the series, you'll be amazed how much you understand. Okay, but without any further ado, let's get into the Bloch Sphere. Very important concept. And the 10 minutes starts now. Okay, so the Bloch Sphere is a very important concept and a way of mathematically distinguishing between classical and quantum computing. Now, on the left, we've got a classical digital computer, which is basically every single computer that has ever been works this way. And that is like a light switch. It's either on or off. It's either 1 or 0. And the way we can physically make it 1 or 0 is by applying a voltage through a transistor. So there's either a voltage there or there isn't. And that's the physical things we do, which then can be mathematically allow us to make computations, amazing computations that we do today. You know, you can search on the internet and get over 1 million responses immediately. And the fastest digital computers at the moment are doing well over 200 quadrillion operations a second. It's amazing what they do. But let's get one thing straight. They pale into insignificance compared to a quantum computer. And let me now explain that. So a quantum computer can be 0 and 1, or 0 and 1 at the same time, or anywhere in between. The way I like to explain to young students is by saying, imagine if I gave you 2 A4 sheets of paper, and you ran and put one on the North Pole and one on the South Pole. That's what a classical computer is like. You've only got 2 A4 sheets of paper at either end of the poles where you can make a mathematical entry, i.e. it's on or off. But a quantum computer, because of superposition, remember the very first video lesson that we did, and superposition told us that it could be in many states. And what happens, for us to be able to map to every single A4 sheet, we could get A4 sheets and put them all over the volume of the Earth. I worked it out as being 8 trillion A4 sheets of paper. But that actually is theoretically what we can do with a quantum computer. We can map to any part of the globe, and we control that with linear algebra. Now, it's important to remember classical can only be linear. It can only multiply, perform computations linearly, whereas a quantum computer can compute exponentially. And to give you an idea of the difference, if I ask you on a table of 10 people, how many different place settings could you have? And just imagine it. So I could have somebody on my left, and then we swap places, and they're on my right, etc., etc. How many different place settings? The answer is 3.6 million. It's actually the factorial of 10. But that's because it's exponential. So the increase in computation is absolutely phenomenal. Here's basically what I'm saying. Instead of only being able to map to 2 points, like all classical digital computers, the quantum computer can map to a theoretical infinite number of locations. And that's just superposition. Remember lesson 2, we did entanglement. Well, you can actually now entangle 2 of these quantum Earths, let's call them, and you can actually start being completely exponential. Okay, we have 4 minutes, 17 seconds left. Let me answer some questions I commonly get, and I'll answer them very briefly. What is a qubit physically? Physically, it's a subatomic particle that is in superposition. It must be in superposition to have the powers of superposition, which behold exponential processing. So it's got to be in superposition. So when you see a quantum computer with a great big huge thing, all it's doing is isolating that subatomic particle so it remains in superposition. What does a qubit represent mathematically? Mathematically, it's represented by linear algebra, by matrices. So you get the state of a qubit multiplied by a matrix, and then you get a new state. Just like a classical computer, really. What is a qubit in a computer sense? It's something that allows us to compute exponentially. How do we put a particle into superposition? Physically, we send a microwave burst of various duration and intensity. Mathematically, we just apply a Hadamard gate. And I'll talk about this later, but if you see the equator on that graphic, that's what superposition is. It has an equal chance of going to 0 or 1 when it's measured. How do we represent any point on the Bloch sphere? Great question. Psi, if you again look at the Bloch sphere to the right, psi is the thing which is like a U dissected by a forward slash. Psi is basically represented by what we call complex amplitudes of being 1 or 0. So that's just the probability of it being 0 and the probability of it being 1. And that's how it's represented. Okay, 2 minutes and 8 seconds left. Yet we can measure it on 3 different bases, which don't commute, which means if you can't know for certain what it is on the x-axis and the z-axis at the same time. When you have more than 1 qubit, that's when the fun begins, because not only do you have this wonderful superposition, but you can also entangle it. And the CNOT gate is a great example of this. So again, a quantum computer just uses logic gates the same as a classical computer. There's the equator again, and that's when a qubit is in superposition. And it is important to realize later, not now, but later you'll see that any point in the northern hemisphere has a greater chance of being 0, and the southern hemisphere has a greater chance of being 1. Again, classical computers can only be 0 or 1. They use logic gates, and a quantum computer can be 0 or 1, or an infinite number of variations in between. And here, from the linear algebra standpoint, you can have a state and multiply it by another matrix to move that, effectively move that location around on the Bloch sphere. And there's the matrix formula for a Hadamard gate. You've got to learn how to multiply matrices together. So have a good look at this slide and see if you can multiply the 2 by 2 matrices to end up with a 2 by 2 matrices. And here are all the matrices for the linear algebra matrices for some very, very important gates that we'll talk about next time. And that's it. We've got 9 seconds left. So please do join us for our next lesson on quantum gates. I hope you're enjoying the series. Please, oh, there goes the timer. Please subscribe to the channel and like the video. It does make a difference. Thank you.